Okay, we're about to do some Doughnut Method reviewing. We did the pancake method recently. This is an extension of that, and again, because you're in BC Calculus, I assume you have some good background knowledge of this, so I'm not going to go as slow as an AB introduction video. We're using the same region as the pancake method, but now we're going to rotate this region about this axis. So when I rotate that axis, bzzz, this figure is rotating around, and it makes a very, very unusual figure. There's my best attempt at drawing that. I think that's pretty good, actually. I'll take that. And what I now have to think about is a slice through the figure that creates a circle. If I were to slice this way through this figure horizontally, that would not create a paper-thin slice that is a circle. But if I slice this way, like that, now I have a paper-thin slice that is a circle. In fact, though, if I take out that paper-thin slice, I would have a hole in the center. This space in the center, which is represented by this, is this open space. So, like your good old geometry days, you have a little circle, that's a baby R in there, I know it's hard to see, and a big circle, that's a big R. And if I want to find the volume of actual material, I have to do the area of the big circle, take away the area of the little circle, and I'm left with this ring of goodness, which we could think of as a donut. So that's what I'm going to do. I'm going to integrate or accumulate along the x-axis from beginning to end the area of a big circle minus the area of a little circle. That means my very first slice would happen right here. My very last slice would happen right here. And we did this in the last video. This would have to be an x value of 2, and that would be an x value of 0. So now we start rolling through. We do the area of the big circle minus the area of the little circle. And this is a dx problem, but check this out now. Oh, and by the way, because I could factor a common factor pi out in front, I'm going to actually move it out into the front of the integral just to make things a little easier on my eyeballs. Now I can concentrate on this. Well, the big radius, which on this picture over here would go out there, which means the big radius in this picture would go all the way up there. That is a pure y value. It goes x-axis up to a function, so I say that's a pure y value. And then the inner radius, the radius of the little circle, would go from the center up to this curvy part, which means it would be like that. So I'm going to call that a little y. That's a pure y value because it goes from x-axis up to a function. So instead of r's, I have y's, but my problem is this is a dx problem, so y is not a welcome variable. I have to turn that into an x variable. The big Y is a pretty easy problem to solve. That's this distance, which happens to be 13. The little y is the distance up to this curvy graph, and since that's a y value, I can say that little y is equal to x squared plus 9. So now I've converted to the dx language, and this is starting to kind of lose your pi r squared minus pi r squared feeling, but if you've done everything right, this really is relaying that, and thus, if you put that ugly thing into your calculator, you will get a volume. I'm not worried about getting the actual number because that's tedious, and very frequently, if this is an AP test question, they want you to write the integral. They don't care about the final answer. But if you're yearning to find out how much volume is in that figure, go ahead and punch that into your calculator. That is the Doughnut method, and it's a doozy.